This lecture is about the operation of single-phase induction motors. In the previous lecture, we mentioned that because of the double revolving theory of magnetic field in single-phase induction motors, there is no torque generated at standstill. So the purpose of this lecture is to explain the various engineering solutions that have been found to enable induction motors, single-phase induction motors, to generate starting torque. Because of the double revolving field theory, the per phase torque generated in a single phase induction motor is given by I squared R2 over S. So the most critical part of this is the slip. Now, we mentioned with double revolving field theory that you have forward slip and you have backward slip. When speed is 0 at standstill, speed is 0, which means that the forward slip is equal to 1 and the backward slip is equal to 2 minus 1, which is still 1. So that means that forward slip and backward slip are equal to each other. Because of this, the value of torque due to forward and backward magnetic fields is equivalent to each other. They are equal to each other because the value of S is the same. So this leads to forward torque and backward torque being equal. That means that at standstill, we have no resultant torque that can push the motor into motion. So how do we generate torque at standstill? How do you get the single phase induction motor to start moving if it has no previous direction? Now we employ a characteristic called split phase. Now if we look at the rotating magnetic field due to a two-phase AC supply, let's imagine that we had two phases that we could put into the same motor, into the same windings. So for example, in this particular instance, this is a demonstration of two different phases being applied in the same space. So you have at different times. So this is at time 1, time 2, 3, 4, 5, 6, and so on and so forth. And back to 1. And those are the corresponding diagrams that we have here. So if we take instant number 1, instant number 1 assumes that you have the first phase, the X phase, with a positive peak being shown there, so that you have the X with a resulting magnetic field in this direction and this direction, which moves in that direction, and you have the Y phase with a 0 value of voltage. That is at instant number 1. At instant number 2, both phases are at positive values. Therefore, they have a resultant that moves in that direction, and so on and so forth. At number 3, you now have the X phase having 0 voltage and therefore 0 magnetic field or impact on the magnetic field, and you have the field going that way. So in the case of two phases, if we could connect two phases to a motor, you'd be able to get the rotating magnetic field in the same way that we have in three-phase induction motors. If we can supply a phase difference between the two, a rotating magnetic field is created, which in turn creates magnetic or starting torque. So how do we do that? There are different ways in which we achieve the phase differences that we are talking about with regards to AC motors. Previously, we had talked of the three-phase. These were what we were calling squirrel cage motors. Those were the three-phase induction motors. And the single phase, which we have over here, now have various ways in which they generate that starting torque. So now in this particular case, we have three main types: the shaded pole, split phase, and capacitor. We will take, for purposes of this discussion, the split phase and the capacitor motors together. So we are going to talk about split phase, capacitor start and induction run, two value, and permanent split. Those are the four types of motors that we are going to talk about within this discussion. So split phase motors have two types of windings. Yeah, you have a main winding and an auxiliary winding, and the way in which these motors work is similar to what you have here. You will have one of these sets of windings being called or designated a main winding, and you'll have one of these being designated as an auxiliary. So in this particular case of the split phase winding, in fact, all of these motors have a main and an auxiliary winding. The currents in the two windings have a phase difference, which is what creates the rotating magnetic field. So what you'll find is that you supply a single phase to the motor itself, but because of the two sets of windings connected to each other in parallel, you will have phase differences between the two, which is what we are going to demonstrate. So the first motor we are going to look at is the resistance split phase motor, which is demonstrated here. This is the general illustration of split phase induction motors, or induction motors in general, which are single phase. So you have a voltage being applied across the windings, and you have a main and an auxiliary winding connected in parallel with each other. This represents your rotor, which is free to rotate within the confines of the two, the main and the auxiliary winding. So each of the windings is a copper winding that are wound together in parallel and connected in parallel to each other, such that you get two different characteristics, two kinds of currents. You have the main current and the auxiliary current, which is listed there. Now, the difference between the two, there are no additional components that are added to these windings. The only differences are in the thickness and the length of the windings. So you remember that if you have a winding, the resistance of that winding can be given by rho L over A. So if you increase the length, you increase the resistance. If you decrease the area, you will still increase the resistance. Or if you increase the area, you increase the resistance. So those are the characteristics that are played with in order to get these two characteristics. So what you find that in every winding, there is a value of the resistance and there is a value of inductance, because it is a coiled conductor. So in the case of the resistance split phase motor, you will have the ratios of the individual windings. The ratio of resistance to inductance or resistance to reactance in one winding is greater than the ratio of resistance to inductance in the other winding. Yeah. So what that leads to is the auxiliary winding, we say, is more resistive, because the ratio between the resistance there and the inductance there is higher, and you have your main winding, which is more inductive, because this same ratio is lower in the main winding. So how is that achieved? The auxiliary winding uses thinner conductors with fewer turns. Yeah, so the auxiliary has a greater resistance to inductance ratio. The R over X is higher. So what does that now mean for us? If you have the phasor diagram of that particular motor. So now you've connected a voltage. We take the voltage as the baseline, which is at 0 degrees. You have your voltage there. In this case, it is called VAC. It is connected across both of the windings together because they are in parallel with each other. The resulting current, the current as seen from the supply, is at a certain angle because the windings have both inductance and resistance. So you have your current I in a certain direction. Now, we said that the auxiliary winding is more resistive and the main winding is more inductive. At this point, you have the main current, or rather the input current I, being equal to IA in whatever direction it is, plus IM in whatever direction it is. All right. The sum of these two results in the I from the supply. The vector sum of those two results in the I of the supply. So in this particular case, you will have your value of IA. Because it is more resistive, the angle is closer to that of the voltage. And likewise, you will have your IM, because it is more inductive, being at an angle that is greater than the two of them. So the resultant, of course, is your I at the supply. Okay. So now if we look at the phasor diagram, we will notice that there is an angle in between the main winding and the auxiliary winding that gives us actually a phase difference. This is the phase difference we were talking about in the previous discussion, whereby as long as you have a difference between two windings, the currents flowing between the two windings are out of phase with each other, you will be able to achieve a rotating magnetic field. And in the case of the split phase, we call this the resistance split phase motor, this angle alpha is 30 degrees. That is the phase difference between the current in the main winding and the current in the auxiliary winding is 30 degrees, and that is enough to give us a rotating magnetic field, albeit a weak one at the beginning. So one thing we'll notice when we look back at the wiring diagram or the circuit diagram of our motor is that we have a centrifugal switch provided at this point. Now the reason for that is you have a main winding that is more inductive than the auxiliary winding. Sometimes we call the auxiliary winding the starting or start winding. The reason for that is the auxiliary winding, as we have said, is more resistive, and that is what gives us the phase difference when we are starting. However, this is a disadvantage when we are running the motor, in that when you have a more resistive winding, you have less of the power being transferred into mechanical energy, and instead it is wasted as heat losses. Now, the idea we would want to have is we want to have our more inductive winding with its thicker conductors and more turns being used more of the time. And that is why we have the centrifugal switch. You only need your auxiliary winding when you are starting the motor. Once the motor has started, it is simply enough to have one of the windings. You don't require the phase difference. The double revolving theory, field theory, remember, states that as long as you have you have a difference in speed between the synchronous speed and the mechanical speed, you will be able to have it. Once it is already moving, that slip will be enough to keep it in motion. So what we end up having is the torque speed characteristic that looks like this. For purposes of the beginning, let's talk of this first part. So the first starting phase of the operation of the motor, when you have from 0 speed up to a certain speed where it is near to its normal operating speed, we have the main winding and the starting winding being used together. If we were to only have the main winding alone, remember, you would not be able to generate any torque at the start. However, because we have the main winding and the starting winding, you are able to have some torque at the beginning, and until the point where we feel we have attained enough speed, we will retain the main and the auxiliary both within the circuit. At this point, once we reach this point, that is where now we have your centrifugal switch that switches out this part of the motor. These windings are switched out of the circuit, and you remain with only the main winding. So that is the running. So that is the running phase of operation, whereby you have your main winding running by itself. And if you look at the characteristic, it gives us a more vertical characteristic along that line, which is our main operating area. If we were to maintain the starting winding or the auxiliary winding in, it would be a gentler slope, which gives us a lower power conversion. So this kind of motor is usually used in low torque applications, such as fans, blowers, and certain pumps, which don't require very heavy starting torque. The starting torque here is just above 100% of the full load torque. Yeah, so it will usually you require a bit more torque when starting in most of the applications. So how do we get a better starting torque? Remember, the angle between the main winding and the auxiliary winding in this particular case is about 30 degrees. Whereas in our previous demonstration, we were looking at 90 degrees. The greater the difference, the greater the phase difference between the two windings, the more torque you will have at the start. So in order for us to do that, let's look at some of the other possible applications of different kinds of motors that we can use, the other possible configurations of motors. So the second kind of motor that we have is the capacitor start induction run motor. Now we will look at three different types of capacitor motor. If we look back at our initial diagram, we had talked of, we have the split phase motor, which we have just discussed, which only uses the windings themselves. Yeah, the resistive and inductive properties of the windings themselves are what create the phase difference and what creates the starting torque. So under capacitor type motors, we will look at three different types. So let's look at the first one, which we are calling capacitor start induction run. So we look at the windings. It's a similar case. You have a main winding and you have an auxiliary winding. And the auxiliary winding has a centrifugal switch. The only new thing that we have here is our capacitor. We have now added a capacitor. And the reason for that becomes apparent once you look at the phasor diagram. So if we look at the phasor diagram, you have your voltage indicated in the same way, and you have your main winding with its current in that direction. The angle is roughly the same as what we had before. You have a very inductive type of winding with low resistance and high inductance. You want to transfer as much as possible of the power to mechanical. Now, what do? We want to have an angle between alpha, which is the angle between the main and the auxiliary. Yeah, and the biggest possible angle that we can have, like what we had seen in the two-phase machines, was 90 degrees. So what we want to generate is, you want to have a 90-degree angle between your IM and your IA. Okay, so in this particular case, what will then happen is you have your resultant IM and IA giving you a current from the supply that looks like that. Okay, and you'll still have your angle looking like that. So now our alpha angle, which we had talked of before, which is this one, in this case, alpha is equal to 90 degrees. So how did we achieve that? Of course, we achieved that by having a capacitor added into the circuit. So you have the windings of the auxiliary in series with a capacitor within the circuit itself. And that then leads to a torque speed characteristic that looks like that. So straight away you can see a massive increase in the starting torque. Yeah, it is over 300% if we have the main and auxiliary windings put in. At the same time, we would then have our starting phase, which is indicated there, and our running phase, which is indicated there. Okay, so this is why we call this particular circuit the capacitor start and induction run, because you use the capacitor in the auxiliary winding at the beginning to create that starting torque, a very high starting torque that you can make use of to start it. And then once it is up and running at a good speed, you can then switch out the capacitor so that you take advantage of the inductive properties of the main winding by itself. So that is the second phase of operation, which is there. So the applications of these types of windings, it is things that must have load at start, so high starting torque. And these are things like ACs, things like compressors, and certain kinds of, water pumps and so on and so forth. This is equipment that needs a high torque at the start. ACs, compressors, fridges, and so on and so forth all require a high starting torque because there is inertia of the load. Such systems need to pump the liquid. So like in the case of compressors, you need to start compressing the liquid when it has inertia. And so that is the main use of these particular types of capacitors. Now, of course, the main disadvantage here of both this type of motor and the previous one is that you have a big failure point in the centrifugal switch itself. And that is a point which you would want to maybe get rid of. So an alternative that we have is what we call the permanent capacitor induction motor, which is indicated here, whereby you get rid of the centrifugal switch and you just retain the auxiliary winding within the circuit throughout its operation. Yeah, so in that case you will have a similar phasor diagram to what we had in terms of having the capacitor inside the circuit. If we go back to that, you'll have a similar phasor diagram to the other capacitor start and induction run motor, and we'll be able to see that that is also the characteristics of the permanent capacitor induction motor. The only difference being your phasor diagram, or rather your torque speed diagram, will look like that. Okay, you will have no starting phase or running phase because all components of the circuit remain within the circuit. Yeah, now you will note that you have a slight improvement. You have some amount of torque at the beginning. However, it is even less than what we had with the permanent, or rather with the resistance split phase motor. The only difference is you eliminate the use of the centrifugal switch that we had with your resistance split phase motor. Remember that in the resistance split phase motor, you needed your centrifugal switch to switch out the auxiliary winding because it reached a certain point whereby the auxiliary winding is detrimental to the operation. But at the same time, you can't have the main winding alone because you don't have torque. So this is a compromise which allows us to have a simpler design, a simpler, more robust design, whereby you don't need a mechanical switch, but at the same time you have a starting torque. So the advantage, a robust design, no moving part, but the disadvantage is low starting torque. So therefore, the application that we are talking about here will be that we have places where we don't require a very high starting torque. So you have low starting torque, but we do require very cheap motors. So that's the main advantage that we'll have here, is it is extremely low cost, since you don't have wear and tear from the switches, and also it is the removal of that particular component allows us to have a simpler and possibly a smaller design. Now the final type of capacitor is the two-value capacitor, or it is also known as the capacitor start and run motor. Now we will have one capacitor that is much larger, and it is used during starting conditions, and we have the running capacitor that is permanently inside the circuit. Now the reason for this is, in the previous permanent capacitor motor, you saw that it had a very low starting torque. Now in order for us to compensate for that, we add at the starting conditions a capacitor that will balance out or increase the torque that we have at the initial conditions. And in this case, you will see that you have a torque speed characteristic that looks like that. And what we'll notice is that this kind of configuration gives us across the board the most balanced level of torque. You will notice that the torque for the majority of the operation, whether it is running or starting, is within the same range from 200 to 300%. There are no wild variations. So this particular type of configuration gives us uniform or regular torque. We can call it, actually, let's call it balanced operation. So it is used in such applications which require a balanced operation from start to finish, an almost constant torque that you can make use of even when you're starting up the capacitors, or rather starting up the motor. Now let's look at an example of the applications of these kinds of split phase or capacitor start and run motors. So here we have a single phase capacitor start motor, which has the auxiliary windings and main windings values as indicated there, 7 plus J5 and 11.5 plus J5. We want to determine the value of capacitor to be connected in series with the auxiliary winding in order for us to achieve a phase difference of 90 degrees. Remember, that's the best phase difference we can get in order to achieve the maximum torque between the two start windings at the start. Okay, so now we have the currents between the two, which are IM and IA. So remember, we said that the vector sum of IM and IA will give us the value of the supplied current. Okay, and we've said that the voltage at the supply is 230. The value of Rm, which is the sum of these two, Zm, the sum of those two, and Za is the sum of those two. So Rm is 7 ohms. Rm. Xm is 5 ohms. And for the auxiliary, we have 11.5 ohms as the resistance and 5 as the reactance. Now we don't know what the value of the capacitor is. That is what we are trying to find out. Okay, so in actual sense, ZA is equal to 11.5 plus J5 minus, remember minus because capacitors are in the opposite direction, so J, X, and C. Now, so in order for us to look at this well, we will need to see what is the phasor diagram of this circuit. So first of all, you'll have your voltage as your reference. Then you'll have IM, which is in that direction at an angle. So the angle of IM between the voltage and the itself and the current itself is given by the phase angle of that particular winding. So let's look at that phase angle of the winding itself. So Zm is equal to 7 plus J5. So if we want to get the angle theta, let's call it theta m of the main winding, we have the complex values 7 plus 5i, and change that into polar coordinates, and it gives us, it is equal to 8.602 at an angle of 35.538 degrees. So that's approximately 35.538 degrees, which is there. And so what we now want to do is to check if what angle will give us IA to IM of 90 degrees. So the angle between IA and IM is 90 degrees, which is equal to 35.538 degrees minus theta A. And that is therefore 90 minus 35.5376779. Therefore, theta A is equal to 54.462. If you have your value Zm, so Za, sorry, is equal to 11.5 plus J5 minus XC. So we note that because theta A is above the voltage, it is actually in a negative polarity. So now the angle theta A, or the tangent of angle theta A, is equals to tan minus 54.462, and it is also equal to 5 minus XC over 11.5, which gives us which means that it is equal to negative 1.4 is 5 minus XC over 11.5. So 11.5 times negative 1.4 is equal to 11.5 times negative 1.4 equals negative 16 16.1, which is equal to 5 minus xc. Therefore, xc is equal to 5 plus 16.1. xc is equal to 5 plus 16.1, which is equal to 21.1. But xc is equal to 1 over 2 pi fc, which means c is equal to 1 over 2 pi f xc, which in turn is equal to 1 over 2 pi times 50 times 21.1. Therefore, c is equal to 1 divided by 2 pi times 50 times 21.1 gives us 1.50, which is 150.86 microfarads, which is our answer.